Okay. Can you all hear me okay?
Yes, I can hear you fine.
All right.
Right. So we now have Bill Geyer giving us a helicopter update for ArduPilot. Over to you, Bill.
All right, thank you. I am the trad heli maintainer, and so basically a little bit about me. Been a flight tester for helicopters with the Navy for the last 28 years, and last 10 or so I've been teaching academics, specifically helicopter stability and control. And basically, as you can see, my passion with the trad heli work has been mostly in trying to improve the handling of the aircraft. And certainly one of the big things lately has been this auto tune, trying to get something workable for helicopters. And please, if you have questions, feel free to stop me during the presentation. So I know I did this last year, but I know a lot of folks may not have as much experience with helicopters, and I thought a brief introduction to rotor dynamics is worthy, only because it helps with understanding of what I'm going to be getting into in the rest of my talk. Then I'll go into kind of some of the changes since last year, kind of listed there, get into the current projects, which I show there, and then finally finish up with some of what we're planning for the next year. So to start into the rotor dynamics, we kind of have to talk about the degrees of freedom of the rotor system, and there are 4, and kind of what each of them add to the control of the aircraft. So obviously the first is the axis of rotation, or basically the rotational degree of freedom, and that's essentially just the the rotor spinning around the shaft, right? Nothing big there to say. One thing is that our model helicopters rotate clockwise when viewed from above, whereas the American-made helicopters rotate counterclockwise full scale. So a little bit of difference there that kind of comes into play with single main rotor, tail rotor configurations because of the thrusting tail rotor. Next, we have the flapping degree of freedom. And that's basically this vertical motion of the blade it can be either done through a hinge or the flexibility of the blade itself, or maybe even some flexibility of a yoke or something inside the hub that allows that blade to flap up and down out of the plane of rotation. And this provides for this is how the helicopter essentially, or the rotor, imparts moments on the aircraft. Now, and I can talk about kind of the 2 ways that's going to happen here in a few minutes. But that's the main reason for the flapping, is trying to create those moments on the aircraft in the pitch and roll axis. The next is the lead lag degree of freedom, and that's this fore-aft motion of the blade, what we call in the plane of rotation. The plane of rotation essentially is a perpendicular plane, or a plane that's perpendicular to the shaft, right? And so this plane of rotation, it basically moves in the plane of rotation, forward and aft. And really it doesn't serve any purpose other than to relieve stresses because of the flapping motion, right? And the reason why we need this, it's a nuisance mode, but the reason we need it is that the blade, as it flaps up and down, changes the rotor's inertia, right? Moment of inertia. And so basically, or I should say the blade's inertia, as it's spinning around that shaft. So as it gets closer to that shaft, the inertia decreases, and so the blade wants to spin faster. So it speeds up. And then as it goes back out to the plane of rotation, it slows down. It's basically kind of like the ice skater effect. You think about the ice skater, they put their arms out, they slow down. As they pull their arms in, they speed up. And that's the same idea there. And that's essentially why we have lead lag. So you either have to, put a pin in there and let it do that motion, or you can restrain it, but you have to account for the fatigue and vibration that you might get from that. And lastly, we have the blade pitch, or the feathering. And basically, this is how the pilot or the flight control system controls the blades flapping. And so you can use the blade pitch to either make collective blade pitch inputs, so all the blades either pitch up or pitch down at the same time at every point around the azimuth, or you can make cyclic blade pitch inputs where one blade will change its blade pitch in a cyclic motion so that it, maybe it's going to create more longitudinal type forces than lateral. So basically that's the idea behind the cyclic blade pitch. And basically the idea for the swash blade is to provide that cyclic blade pitch motion. So a little bit more about, our RC helicopters and kind of this idea of a teetering rotor head. And so you can see here at the bottom, this axle pivot and the spindle that goes through that. For modern full-scale helicopters, they actually allow this axle pivot for a teetering rotor system. It's actually freed. It can actually, the blade can actually flap up and down like 12 degrees or so. Whereas for most RC helicopters, they add this solid head, this head dampener. Essentially, it's a piece of rubber or plastic or something that's put in there to restrain that blade motion, and it stiffens that response in the head. And so it changes the dynamics of the rotor. It makes the rotor much more stiff. And then you can see that those cases for our scale helicopters, our lead lag is done through the blade grip and the pin that mounts the blades on there. It basically provides for that lead lag degree of freedom. So let's talk a little bit about rotor phase lag, because that has a big impact on the dynamics. And essentially rotor phase lag basically says that, with the rotor spinning, if you make a cyclic input so that your max blade pitch, and let's say call it an aft longitudinal cyclic input, so elevator input. So when we pitch the aircraft up, you'll have your max blade pitch over on the left side of the rotor system, like on the left side of the aircraft, because you're spinning around in this direction and you want the response of the blade to flap up. And you would have the min blade pitch on the right side of the aircraft, and then you want the blade to flap down. And we say that the response is not going to happen until 90 degrees after the max input is made, or minimum input. So for a teetering rotor system that doesn't have any type of stiffness in it, it's a free teetering rotor system, you're just basically get an aft tilt of the rotor system. And then that produces a moment, because it doesn't have any type of connection moment-wise into the shaft, it's basically just tilting that tip path plane back. And our thrust vector, we say, is perpendicular to that tip path plane. And so that then just causes this moment about the CG for the pitch motion. And that's different from, kind of pull this out, that's different from the multi-copters, right? Because basically their assumption is, or basically the thrust is always perpendicular to the shaft of the motor, or basically the vertical axis of the aircraft. Whereas in our case, the rotor in most cases can kind of change its tip path plane relative to the body, and therefore you can change that thrust vector as well. And so when you add a stiffer rotor system, add a little bit more stiffness in there with those dampeners, then you become more of this hingeless type rotor system. And now, because of that, we tend to see the rotor phase lag will decrease, will be less than 90 degrees. And so now our max blade pitch inputs, if they're done at the left side of the aircraft, and the minimum's done on the right side, then it's going to be something less than 90 degrees that you'll see that black max blade flapping. And so the tip path plane will actually not only tilt aft, but it will tilt to the right. And so you see a lot of coupling that'll be involved in the rotor as well in that case. And so with my one helicopter that I had, it was like 70 degrees from as far as the phase lag. And so what they typically do is you could take and change your cyclic or your swash plate and rotate it so that your max input's being made, that 70 degrees prior to when you want that pure control output. All right, so that's like 10 minutes introduction to rotor dynamics, not bad. So now we're gonna go ahead and jump into the changes since last year. And you can see there we got 3 that I'm gonna highlight, some with dual heli enhancements, talk a little bit about the improved integrator handling that we did, and then also talk about improved CITL rotor dynamics model. That was kind of the preparation to get into auto-tune. So dual Heli, if those that aren't familiar, basically is this motor mixer for the traditional helicopter, which allows you to control tandem-like helicopters, so Chinook-like helicopters, where the one rotor is in front of the other. And then it also allows you to control transverse or side-by-side configurations where maybe I can say like a V-22 style, where but minus the nacelle tilt. And so the way they control the axis that those rotors are on. So the tandem rotor, the rotors are on the longitudinal axis, and so they're used to control pitch through this differential collective pitch. So the aft rotor system, if you want to tilt forward, the aft rotor system is going to increase its collective pitch. The forward rotor system will decrease its collective pitch, and that'll cause a moment to pitch the aircraft forward. And then likewise, same idea for the side-by-side configuration. And that's how you control the roll axis. And then we have two others, and I'll talk about the intermeshing, but they can use differential collective pitch in there as well. But in any case, so the big enhancement here is that previously when, and this came about because of a user in Germany, he flies Chinooks, scale model Chinooks, and so he was having difficulty always finding it. You have to trim all three of your swash plate servos in order to make sure that to fine tune the difference between the two, in case you're getting some sort of offset that causes some pitching moment. And he said it was just difficult. So we put in a new parameter that basically allows the user with one number to be able to scale the difference between the swash plates and trim out the swash plates better. Great improvement here, enhancement was this was the adding of the intermeshing configuration. Really cool work done by Pitt. He about 2 years ago he started this, and he wanted to make this intermeshing rotor system vehicle, which essentially is like the full scale, if you've seen Command, K-Max, is an intermeshing rotor, or the Husky. Those are full scale intermeshing rotor configurations. And essentially you have these two shafts, and the two rotors, two bladed rotors, are angled very close together, but they're angled such that the rotor system of the one rotor can pass over top of the shaft of the other, and they're then synchronized so that they can intertwine like that, or intermesh. And so he went and actually, I think he pretty much designed and built this whole helicopter from scratch. So it was really impressive, aside from the rotor systems, but just all the mechanics and stuff he did himself, which was really impressive. And he then built the motor mixer that he needed to control it. And so thanks to him for pushing that forward as a PR to master, that we were able to then get merged. And kind of the offshoot of that was the fact that I realized that with his work that he did here, we could use one of the parameters that would let us then now also control coaxial type rotor systems. Previously, coaxial rotor systems, shown over here on the right, they're done full scale mainly with like what they called like a ganged swash plate configuration. So the swash plates are interconnected, and they're mechanically linked and mechanically mixed. And we could still do something like that with our code, but that's not what we wanted. We wanted the ability to control each of those swash plates independently. And so like with this helicopter here, or this coaxial system here, you have the motors that's turning it, but you have two independent swash plates, one controlling each of the rotor systems, and that this coaxial, the new intermeshing motor mixer can allow us to do that. Right, so integrator handling. So, the integrator is responsible for that long-term matching of the requested rate, right? Trying to keep them, if you're requesting 0 roll rate, the integrator is going to work if there's some disturbance over the long term to kind of help you maintain that zero roll rate. And so prior to this change, the way that Trad Heli had done its integrator was to, reason we have difficulties with integrators because we're always rotors turning on the ground. And so the users would have issues where, too much I-term would build up and it would then basically drive the rotors into the dirt. So we had to find a way to limit the I-term while you're on the ground. And then when you get up and away, then allow it to build so that you can, basically oppose any type of forces that develop and you want to, to get your, the long-term rates where you need them. In any case, so what happened with the integrator is that it remained, you first turned it on and allowed it to build when you started spooling up the rotor. And then it remained active until the aircraft was disarmed. So not only until it was motors interlock disabled, but after you disarm. The reason being was if you ever were to go and pull the motor interlock off, like turn off your motor in flight, which we could do for an auto rotation, you don't want to lose that stabilization. And that's why it was done that way. And then one other thing is again, like I said, we wanted to limit the amount of control on the ground. So we used this ILMI parameter, right, for less than 5 knots. And that was kind of the minimum leak is what we called it value. And so, as the integrator would build up, if it went above this minimum value, it would be leaked off. And then when it went below it, or if it, it would just leak it down to that minimum value, it wouldn't let it get any larger. So if you were sitting on the ground on an angle, then it would just limit it and you wouldn't cause the rotor to be driven into the ground by the flight controller. But then greater than 5 meters per second, it basically allows it to go to IMAX value. So in 4.06, I took and talked to Leonard a little bit and learned off of him and basically kind of learned how to invoke the multi scheme. And so I did that, and you can now have H options. I did it as an option for our users because this new technique relies heavily on the landing detector. And so we needed to really be able to trust the landing detector. And I've heard of instances where for helis, because of the large vibrations on the ground, that sometimes the landing detector isn't always trustworthy. So I just wanted to make sure users had the option at first to try this out if they trusted their landing detector. So what this new, what I call it an improved integrator scheme does is, like I said, we leveraged off the multi-copter integrator handling. And it includes the use of that multi-copter hover throttle feature, which now I call hover collective for helis. And again, like I said, it requires the accurate landing detection. But I also added, I don't know if any heli guys out there realize that, when they landed maybe in loiter with the old system, right, you'd land and maybe you're on an incline or something, and you'd see the rotor kind of all of a sudden just snap back to kind of center itself. That was actually the I gain being taken off and reset instantly to 0. And so, that wasn't very kind to our helicopters. So I basically decided to put a decay in there since I was messing with it. And that smoothly resets the integrator. So here's kind of a show of how during takeoff, the integrator handles itself. And so unlike previously where we turned the integrator on when they started the rotors turning, here the integrator stays clamped at 0 until it detects takeoff. And how does it detect takeoff? Well, it looks for when the collective is raised above 50% of the hover collective, and then it releases it. Now over here, you can kind of see that it kind of got released a little early. This is in alt hold mode. And you have to remember that in alt hold mode, it says it's not landed as soon as you start requesting a climb rate. And so that's what happened here is it started requesting and it kind of released it but then it clamped it until it saw the hover collective was above 50% and then released it. You can see that gives a really nice climb, and the aircraft lifts off and matches the requested attitude very nicely. And then for landing, again, it relies heavily on landing detection. And so hopefully you can see the blue line here because that's the integrator. But basically, you can see the red and green track together, and then on touchdown, as the one skid touches, and then the aircraft starts to roll, you can see it's rolling over to basically sit with both skids on the ground, and so you get this error in attitude, and now the integrator starts to build. Now, when the landing detector says, "Hey, I think we're landed," and it invokes the land complete maybe flag, it freezes the integrator at that point, and then once it says, "Hey, yeah, I know I'm landed," and then it will then smoothly decreases that integrator value over a half a second, and then resets it to 0. Hopefully, any questions on that? Any questions so far? All right. So the other enhancement over the past year, like I said, as I was getting ready for auto-tune and trying to develop the auto-tune, I decided that I needed to have some sort of simulation that would be accurate enough to test the auto-tune before I went into flight. And I realized quickly that real flight rotor dynamics are not modeled very accurately. So I had to go in and develop, I was at work, I was doing this type of work anyway, developing a rotor model for a helicopter. And so learning off of that, I was able to go out and do the flight test on my scale helicopter, my RC helicopter, and gather the data and develop that model. Right now, the model is only flapping dynamics, and that basically accounts for that coupling that you saw for a stiff rotor system. It captures both the on and off axis rotor dynamics. The flap regressive is one of the two modes of the rotor that are mainly responsible for that feedback instability that you see. Typically, when you increase your gains too high, you'll see the aircraft start to flop around or oscillate pretty heavily. And that's typically when you're tickling that flap regressive mode and destabilizing it. You'll see that. And again, like I said, that it was developed from a 600 size Heli that I own. I used it for both the single main rotor and configurations, which are the conventional and the compound options for SITL. And I fixed the rotor speed at 1500 RPM for when it was in flight, that was the operational RPM. And then it does a spool up and spool down as well. I also modeled the rotor torque effects, fairly simplistic model there, and pretty simple model for the yaw dynamics as well. So, but this down here shows the magnitude and phase for, this is like a Bode plot. And we'll get a little bit more into this in the talk here in a few minutes. But basically you can see the dotted line is my model. The solid line is the actual aircraft. And it matches fairly well. This is 10 radians per second here, 20, 30, 40, 50 radians per second out here. So it matches fairly well up to 4 or 5 hertz for this model, especially in pitch. Now you can see in roll, we start to lose, it doesn't model this very well upwards at these higher frequencies. Well, what that is out there is that the lead lag regressive mode. That's a different dynamic mode of the rotor. So that lead lag motion of the rotor can be excited and also become unstable. And at first I didn't model that, but then I found during my development of auto-tune that was pretty important to model, and I had gone back and done that. But right now in SITL, the master has this model here, and I plan to improve that model.
Bill?
Yes?
Sorry to interrupt you, but it might be just worth telling people how you collected this data if they wanted to try and do, there's a lot of interest in people sort of characterizing aircraft similarly to what you've done here. Maybe it's just worth quickly telling people how you collected that data.
Sure. And this is a plug for Leonard as well, as far as the using the frequency response, essentially the new mode, the SysID mode that was developed. Basically, you can use that SysID mode and do frequency sweeps, essentially oscillating the aircraft side to side or forward in one of the axes over a range of frequencies that you're interested in learning the dynamics on. And so then you basically get the frequency sweeps, the frequency responses, and you have to decouple those responses. So there's a little bit more to it than what I'm saying here, but basically when I originally got this data, I actually wrote my own frequency SysID because I actually did it without having the feedback loops. The PID loops were all 0, and basically did it that way. And so basically you go and you gather that data, and you come back and you use your favorite FFT or your spectral analysis software. I use Cypher. You could use MATLAB, and basically you can develop a model of the helicopter based on those frequency responses, and that's how you kind of go about that. But again, if you're going to use the SysID mode, you're going to have to, because you have some of those feedback loops, you're going to have to decouple the responses in order to develop a raw model for the aircraft, basically a bare aircraft model, which is what I had to do for this, right? I needed a bare airframe model. Questions
hey, Bill,
on that?
Hey, it's Matt. I just can ask a quick question about that.
Yeah, go ahead.
Coming from a position of complete ignorance with this the system ID stuff, what I was just wondering about, when you're trying to capture the model damping, are there limitations on the damping that you can capture with this methodology? Is it something whereby your damping, has to be scaled in proportion to your mass and stiffness of your system, or can you get something a bit more clever in terms of the damping you're trying to capture?
Well, it kind of falls out from the frequency response for the aircraft configuration. So I did one for a multi-copter, and when the class I took on Cypher, basically I learned that the dynamics that it can't see. So what you learn quickly is that because multi-copters pretty much have fairly low damping because they're effectively unstable, right? If you don't have any type of help from a flight controller. But basically, when you go and do the frequency sweeps, that kind of falls out of this methodology as to what you're gonna set. What you have to do is you have to, when you ID it, you have to set a structure for your model, right? You're gonna say, well, it's gonna have speed stability derivatives, it's gonna have damping derivatives, it's gonna have control sensitivity derivatives, and you kind of set the model based on what you know is going to be in the aircraft. And then you kind of go through the process of what Cypher allows you to basically identify based on the frequency sweeps what those are, the frequency responses, what the derivatives should be, right? And in some cases it'll say, hey, yeah, no, this is insensitive. You don't have this, it doesn't see that response in the aircraft. And so it'll tell you that it's insensitive to that particular derivative. And so then you basically make the decision, if you believe that that's the true, and in my case, when I did the Y6, I found out that, yeah, multi-copters don't have damping. And so basically, or very low damping. And so you basically just remove it from the model and then continue with your identification. Does that answer your question?
Yeah. No, that's great. Thank you.
Okay. Right. So that was the CITL helicopter model. And like I said, I kind of went along and improved it as I went into the auto-tune work. Okay, so on to my current projects. And two of them here. One is the improved rotor speed governor. About 2 years ago, Chris Olson, who was my co-maintainer at the time, he developed a rotor speed governor, internal rotor speed governor for RG Pilot. And huge success, really advanced the RG Pilot for combustion engine helicopters to have that internal rotor speed governor. And he went on to enhance that even more in a new improved version that we are getting ready to push and merge to master. So basically, what this does, the enhancements are, is that it allows for this automatic spool up and governor engagement. And it actually, monitors the response of the rotor during the engagement, the governor engagement, so that if the motor kind of coughs a little bit, it's going to, manage the throttle to then help bring the engine up to speed if it can. He designed it to maintain rotor speed within 2 RPM with the appropriate settings. It's got an automatic spool down that allows this cool down period for combustion engines, includes that. And then it also includes this rotor speed sensor fault detection logic. So if you have a high side governor failure or a low side governor failure, you can, it'll basically fall back onto the throttle curve. So the design based on, he had done it based on mechanical governors. It only uses a proportional controller based on rotor droop, basically rotor speed error. And I say the throttle curve is used somewhat for feed forward input, but he says that it really isn't required. It can run without the throttle curve, but it's always a good thing to have that throttle curve in there, because again, if you hit some sort of high side or low side fault, you want that throttle curve there so you can basically be able to come home, even though your rotor speed might not be, dead on. At least you're able to fly the aircraft home and land it. It does require RPM sensor, of course, and this governor has flown, he says, over 1,100 hours on helicopters that he used in his business under a modified branch that he was working off of for Argycopter. So a big thanks to Chris for this contribution. Again, it's going to help out advancing our ability to support combustion engine aircraft and get ourselves to this automated startup and shutdown with Argycopter. So the spool up, I have shown it here just to give an example. This is from, I did this with real flight. This is actual real data. I used, I can't remember what helicopter type it is in real flight. But in any case, it had essentially a simulated combustion engine. And basically, you enable motor interlock, and that initiates the spool up. And so what the logic does is it basically increases linearly the throttle along the throttle curve until it gets to 50% rotor RPM. And then it engages the rotor governor, which then, again, like I said, monitors the rotor response and then adjusts as necessary until it gets within 2 RPM of the desired rotor RPM, and then it goes into the governing phase to maintain RPM. And then when you disable motor interlock, it initiates that spool down and cool down period. Throttle is reduced to 1.5. So if you set the cool down to some time, it'll set to then, and during that, that's a parameter. And so if you set it to some like 30 seconds or so, then it basically goes to 1.5 times the throttle output for idle. So H idle, or HRSC idle is the parameter. And so basically it was 1.5 times that for that specified cooldown period. The big thing to remember is that you want to set your spool up time or your rotor run up time long enough so that, because it uses that rotor run up time to then dictate shutdown time. And so you want to make that long enough so that when it goes to do the shutdown, that it actually allows the rotor, or allows the throttle and the engine to cool down before it goes to ground idle and then shuts down the aircraft if you're in an autonomous mode. So that's the big plug there. What I really want to do with this is make it, when you have an RPM, make the spool up and shut down dependent on the rotor speed rather than the timers that we use right now in the rotor speed governor or the rotor speed controller. And so you can see that it spools down. You can see the idles of 1.5 times the cool down period here. You can see, and then it finally goes down to the idle output. All right. So on to auto tune. Pretty much been the last 10 months of my life, weekends and nights working on auto tune. It's, we know that helicopters are a little bit more difficult to tune. And why is that so? Well, if you look at the plots over here, we're talking, again, this is frequency domain type look at the response of the aircraft. So on the x-axis, you have the frequency in radians per second. On the y-axis here for the top plot, it's magnitude. So it's basically the output response, which is maybe it's pitch rate over the input, which is the control input, or I call it the control output, but basically it's the control that's applied to the servo, and it's divided into the pitch rate response, right? And it's instead of a ratio, it's actually displayed here as in dB, so it's just a conversion to decibels. But that's the top plot here. The bottom plot is phase. And effectively, you can think of it like the phase lag of the rotor system. It's not, but you can think of it as phase lag of the rotor system. It's the response, the output response relative to the input as far as the phase. And so kind of think of these both if you're looking at how you're controlling an aircraft, right? And let's say you're making some pumping, pitching motions into your stick, right? And you do it at a certain frequency. At lower frequencies, you'll notice that the aircraft will maintain the same amplitude that you're basically pumping the stick at, right? But then as you increase your frequency, you'll see that the amplitude will start to actually die off as you go to higher frequencies. And that's effectively what that's showing here, is that as you go to those higher frequencies, your amplitude ratio or your magnitude is going to die off, your gain. So now phase kind of describes this idea that as you're making these input, let's say you're in stabilize, right? And so you're commanding attitude. So your stick directly relates to the attitude of the aircraft. Well, at low frequencies, right? It's going to basically match the input of your stick. The attitude is going to match. But then as you get to higher frequencies, you'll see that the aircraft will actually start to get out of phase with your hand, and maybe even go to like being totally opposite to what your inputs are at higher frequencies. That's what this is describing down here. And so at these higher frequencies, you see that it's 180 degrees here. That would be when at this frequency, 10, 20, 25 radians per second, maybe 4 hertz, it's going to be 180 degrees out of phase. Not that you could actually pump the stick that quickly, but your flight controller can, your autopilot. So kind of the quick frequency domain discussion there. So why is it so difficult? Lightly damped rotor modes, right? We have this flap regressive mode that's sitting right here. And when you see this peak in the Bodie plot here in the gain, that essentially is indicating lightly damped mode. And as this peak grows, that means that the mode's getting more unstable. And so this is your flap regressive, and then back out here, and this is the roll response. This is your lead lag regressive, right? You can see that peak out here. And so we can actually excite that as well with our feedback loops. And you can see it also in the pitch axis, but it's at a much lower gain because pitch has higher inertia for our traditional helicopters. So we can't use enough rate P to, because we're going to destabilize the rotor, we can't get that rate P high enough to get a good response to control the aircraft well. So helicopters rely on feed forward, right? Rely on that feed forward gain. And essentially that's just like stick to swash plate. That's all it is. There's nothing being fed back. You're just putting a straight gain into the swash plate to then command a rate. And so that's what that guy's doing. And so in the perfect world, right, we could fly a helicopter strictly on feed forward gain if we had no disturbances. And it responded exactly accordingly to that, right? But of course, we have nonlinearities, and we got disturbances. So we need to somehow force that rotor to respond, or the aircraft to respond to that feed forward request, or to our request. So in those cases, we try to use angle P integrator to help keep the aircraft to maintain the attitude we request. So, ask Leonard. We can talk hours about, what makes a good tune, right? What are we really looking for when we look for a good tune? And, it comes down to this, right? Actual attitudes match closely to your desired attitudes. So how close? Well, that's a good question, right? 1 to 2 degrees maybe can be a really good tune. Leonard with some of his racing quads probably can get into a degree or so, but basically you want it to match very well so that the controller has good sense of where the aircraft is at. So the other thing is good disturbance rejection. What does that mean? Well, if it gets hit by a gust, it's not going to cause the aircraft to go off of the attitude very much. If you're commanding a response, right, you don't want very much overshoot in the response. So if you want to go to 20 degrees instantly, you want it to pretty much come up to 20 degrees and maybe overshoot a little bit, maybe a degree or two, that would be okay. But you want it to nail that 20 degrees as quickly as possible. And then lastly, that the response remains in phase with your desired response, that what you're requesting, the aircraft is keeping up with you or keeping up with the controller request. And so those are the things we kind of want out of a good tune. And so we can kind of see this in our Bodhi plots. And the way we see it, so this is a manual tune of my Synergy helicopter. And this is, Leonard and I worked on this for a while, and this is where we got it to as far as, and we thought it was a good tune. But you can see that there's still this kind of, you could see this slightly, up at the higher frequencies, you're going to see a significant amount of overshoot because of this. The gain is so high here, because this is basically comparing the output attitude to the desired attitude over different frequencies. And so you can see that you got some response that you're going to have some overshoot at these higher frequencies, and then you can see the phase dropping off. So it may not stay in tune, in line with your requests as well. But that's what I have good for. This is kind of I don't want to call it the standard, but this is essentially kind of representative of a good tune for a helicopter for the Bodhi plot. What you really want is that, right? You want this flat at 0 dB, basically a 1-to-1 output based on input. You want this flat across the top here, and then it rolls off, but you want this roll off to happen out as high a frequency as possible. As high as you can get it, you want that roll off out there. And then the phase, you want it to stay near 0 degrees phase as far out as you can, and then roll off. And so that's like, where you want your tune to be. But it sounded, looking at my tune of my Synergy helicopter, it looked like that wasn't where we could get to with a helicopter tune, but we'll come back to that. So the tuning approach here is that you want to go and identify your feed forward gain, and I'll show you real quick, or in a few minutes, kind of where that is, what we do to do that. And so you're basically going to use a time domain test, and you essentially put in a rate response or a rate request, and then you see what the output is. And we can do it with the PID gains on, but effectively this is just what you're really trying to do is determine what that feed forward gain should be to get the desired response to match the actual response, or the actual response to match the desired response. And so here's a little black magic, right? So we want to determine what the maximum rate P and maximum rate D gain is. When we go out and tune our helicopters, one of the scariest things we do, or to even tune any vehicle, right? One of the scariest things you're doing, right? Most users would deem this as being scary, is to go and increase your rate P or your rate D gain until the aircraft starts oscillating, right? That can be a little, unnerving for some folks. But you don't have to do that. You can go and use control theory and be able to oscillate the aircraft at different frequencies, find the frequency that causes a 180 phase between the input and output, and then be able to do kind of close the loop analytically and determine what these maximum rate P and rate D gains can be through flight test. And so I'll show you in a minute about that. And then you can use that knowledge to then, at least know where you don't want to go. And then kind of it's like, well, okay, what's a good value, right? I've found that a good, starting value is like 25% of maximum allowable for the rate D gain. But really, I don't have I haven't come up with a good process yet to kind of determine where is the optimum D gain or P gain, rate P or rate D gain. So, and the other thing is you could excite other modes, right? Right now I'm looking for, the frequency that's results in a phase of 180 degrees. But I could have I could excite the lead lag dynamics at higher frequency at like 9 hertz, where I might be looking at 4 hertz for this, to go unstable. So anyway, another frequency domain test that I use. And then lastly, it's angle P, where we basically look at increasing, increase the frequency until we find the maximum gain. And so that's going to be for the actual attitude divided by the desired attitude. And then increase the angle P term until your gain is no more than 2, which results in about a 6 dB change. So, we're looking for this to be no higher than 6 dB, which is right here. And that's effectively what how I'm tuning that there. Questions so far?
Bill, it's Paul.
Yeah, Paul.
We've got a PR in progress at the moment that looks like it's going to improve the limit cycle protection with tuning P and D on PIDs. So doesn't take away the risk completely, but it makes it a less scary place to go.
Yeah. Okay. Yeah, I mean, yeah, I remember seeing that type of work that I guess Tridge was doing, and he told me about it, and I don't know if Peter Hall was involved with that or not, but basically I did look at that a little bit, and certainly, yeah, I see how it allows you to kind of creep up against those limits, and certainly allows the users to go out there. I guess I was looking, I can for the auto tune feature here, we can at least do that test and be able to know where we don't want to go.
Yeah.
And then now it's a question of where should we be, right? That's the bigger question. So I'm really not looking so now it's something more fine. I'm looking for something more fine than limit cycle oscillation. I'm looking for, what gives you the best response. But I've heard that it was coming down the pike, and that's a cool feature to have. All right. So now with the different tuning types, the feed forward, like I said, is just a straight time domain type test. And it especially involves a single oscillation where you're rolling, in this case, using the roll axis, you roll left 20 degrees, you roll right 20 degrees, and you come back to wings level. And between the 20 degrees left to the 20 degrees right, you want the aircraft to produce a 50 degrees per second roll rate. And so you look at the roll rate it produced, and you take the control output of your, essentially it would be R out from the motors library. And you are able to divide the actual rate into that in radians per second. You can come up with your feed forward gain. And then what it does is it then goes through and that calculation the first time it does it, and then it refines it. If it doesn't get it exactly when it tests that new gain, if it doesn't see that it matches exactly within 5%, then it'll increase or decrease the gain, feed forward gain, until it matches within 5%. It's done in both directions, and then the gain is averaged. And so here's a plot of that tuning, the feed forward, and you can see this is showing the roll angle, and then this is showing the rates, And you can see as you're going from that left 20 degrees to the right 20 degrees, it comes up on 50 degrees per second, and you're looking to see how well these match there. And so that's how that's done. So finding maximum gain, again, we use this control theory to then look at open loop data, where we basically, if we look at this control law diagram here, a real simple one, we have our input, we have aircraft dynamics, and we have the response. Now that's the open loop. That one line there is basically the open loop control of the aircraft, right? And then we can close the loop by wrapping around the response and feeding it back into the input. And that would be our closed loop system. So the open loop, we just basically will control the aircraft and put in varying frequencies until we see the 180-degree phase frequency. And then we can then go through and analytically close this loop based on that to then determine what our max gain would be. That would give us 6 dB margin with the instability. And we can do that for both the rate P gain, which looks at the roll rate response to the R out or P out, whatever that control output is to the motors class. And then we can also do rate D, where we're looking at roll acceleration to the control output. And I do that by mathematically with the in the frequency domain, rather than just actually looking at straight roll acceleration. It's just too hard. So we just do a mathematical version of that based on in the frequency domain. So here's our response. Here's basically the input here at plus or minus 50 degrees per second oscillation. And here's our response. Or I should say this is our input. It's not actually 50 degrees, but this is a VFF here. It's scaled, or the control output, I'm sorry. It's the output scaled from going to from the motors to the servo. And then here's our response output. And you can see the difference in gain. So then you come over here and you can find kind of where you are. This is a 4 Hertz. So we come up here to 25 radians per second. And so we're kind of right here, maybe this point right here. And so that's our gain, is the magnitude of these two, one divided by the other. And then the phase, you can see kind of here, the peak here for the input, and then the peak there for the output. You can see it's probably near 180 degrees. And so you kind of come down here and you go to 25. And sure enough, yeah, it's a little less than 180 degrees there. And so basically, that's what we use to then determine those maximum gains that you can drive the rotor at. Actually, interesting enough, this is the frequency sweep data in the solid line, and this is my dwell data and the points. And you can see how well they do match between the two. So the rate P, rate D, angle P tuning, still a little fuzzy right now, trying to really figure that out. Rate P and D is kind of the next one that I would do if I was going to do a full tune, starting with the rate D probably. And basically you look at the frequency that results in 180-degree phase lag. And then we can start from the one where we determined for maximum gain, but now that we added rate D, so we'll add like 25% rate D, the maximum gain rate D. And so then we go in there, and since we added that rate D, it actually shifts that 180-degree phase lag. It actually goes to the right. So we have to go fat and higher frequencies and find it again, and find that 180-degree phase lag, and then look at what the gain output is, and then kind of change that's a gain response gain, and then we can change the actual rate D again and see how that output response gain changes. And kind of what's fuzzy right now is kind of like, oh, where do you stop, right? You're making inputs, you kind of see the change, and kind of what I'm thinking right now is that when it's, you get the initial value and you say, well, if it keeps on decreasing or stays the same gain value, then I'm going to continue to push rate D gain up. But once that starts to climb again, I'm going to stop and call that my optimum, I'll call it rate D. And then you can do the same thing for rate P. And then with angle P, we basically look at, increasing frequency, looking at the maximum angle or the angle response to the angle request and seeing where we have the maximum gain, whatever frequency that is, and then increase the angle P gain until the response gain is around 2. That's kind of my current thought. So status, we, like I said, a lot of work over the last year, separated the auto-tune library into subclasses, made a generic tuning structure because it was all Twitch, which was essentially for multi-copters. I've maintained the tuning flow, kind of the whole idea of waiting for level, testing, and then updating gains type idea. That's all stays the same. Really no functional change for multi-copter. And I actually went back and tested that, went through a fairly extensive process to validate that. And thanks to Randy for helping me kind of look through the code and making sure I didn't make any mistakes in doing the separation. I got added CITL Heli dynamics to include the lead lag regressive. I've developed a required test type, so I've kind of fine-tuned my feed-forward test, the dwell test for both rate and angle. That's doing well and does a good job. And then the developing of the gain tuning routines is kind of where they're still a work in progress. So recently, and I added this feature, right, that allows the user to actually fly during the angle P test. What I found was during these dwells, since they took a little while, maybe 10, 15 seconds, the aircraft would kind of drift. And so I basically put in a feature that allows the user to come up on the controls within 5 degrees, as long as they're requesting less than a 5-degree angle change. They can come up on the controls and kind of help keep the drift of the aircraft pretty low and keep it in one spot while it's doing its dwell. And so that worked out fairly well. I did provide an initial alpha level version for users to start testing. I only gave them the feed forward and angle P tuning features, and had some limited success. I think the big thing behind that test was basically to learn about other size helicopters and what their responses are going to look like. And so, the feed forward test, I learned a lot off of that, and kind of I was a little too aggressive, so I've modified it to be a lot better. And then the angle P kind of gave me a first look at some other helis into how they look in their response, especially the smaller ones, which I don't have much experience with. Recently, I added a bit mask to allow kind of the ability to specify what tests you want it to complete and the sequence. It keeps the same sequence. It just allows you to pick and choose which ones you want it to do during that sequence. So you can have it, if you know what your feed forward gain is, then you can basically take that out and let it continue on with the rest of the tests. And you can, again, cut out different things. So I think it is, for at least for now, it provides a little bit of flexibility in looking at some things and testing. All right, so here's a video of early on doing the feed forward test and the angle P test, and kind of give you a first look at what that's going to look like in flight. So hopefully you guys can see this. You'll see it'll nose forward and kind of then nose back and then nose forward. And so I reposition the aircraft. There it goes again, nose back, nose forward. Now again, I've changed this so it does it in both directions. This is for early on when it only did in one direction. So it found the feed forward, it's happy with it. And so now it starts going into this low frequency, half hertz dwell, right? And so I'm using my stick to kind of keep the aircraft in one place. You'll see that I think I get distracted and it kind of floats off in one direction on me, and I end up having to bring it back. Nope, see, I paused it there because I'm moving it back. I kind of got it back into position. And so now I kind of have to let it start over again. And so for the angle P, it's kind of tough because it has to actually go through a fairly large range of frequencies to really look to see where that maximum gain is at, what frequency, and then it then increases the angle P gain value to then tune it. Are there any questions? I mean, I kind of, this is going to go on for another minute or so. There it goes, getting a little faster.
I got a quick question, Bill. So,
Yeah.
you see, I take it, are you actually changing any of the gains here, or are you keeping your P gain the same and just oscillating at different frequencies to characterize it?
Yeah, this great question. So this first sequence of frequency is essentially doing a spot frequency sweep, right? It's keeping the angle P the same for this whole entire sweeping of the frequencies. And then it finds that frequency that's, it sees the maximum response at, and it goes back to that one, and then starts increasing the angle P gain for that response.
This is
that frequency.
Yeah, this is very similar to what the system ID does as well. It runs through a sweep of frequencies. And so Bill's basically doing a little mini system ID here to pick his frequency he wants to operate.
Yeah, and so plug to Andy Piper, right? If you want to develop a spectral analysis that can happen behind the scenes, right? That would be awesome on the controller. That way we can then use use the that peak picker that you have. Basically, you're picking the peaks from the FFT. That would be really incredible. That you could essentially do what Leonard's saying, this frequency sweep without having to stop at each frequency. Basically, just do a continuous sweep of the frequencies, and then do the spectral analysis on board the aircraft, pick the peak, and then go back to that frequency and change your gain. And you can actually then, at that point, kind of get a full picture of where you might be seeing kind of another instability kind of rearing its ugly head at another frequency. So yeah, that was something I think I talked to Tridge about that briefly, but it was kind of one of those things that have to be a separate thread, and then it have to run. And I was like, oh.
Because we actually do a chirp as a chirp, we may not need to do anything near that complicated to do that. This is where, Paul is probably best placed to sort of talk about that. But we're already in the frequent. Well, I don't know how to say that correctly, but because we're doing a chirp, we can probably do a constant readout of magnitude versus frequency, because we know our instantaneous excitation, it's just moving.
You need to do a slow chirp for that method to work, because with the second order system and a light damped mode, it takes a few cycles for the amplitude to build. Yeah. So yeah, you'd have to slow the chirp rate down.
Yeah, and that's why you see it oscillates for about 10 cycles, because I'm letting it only really takes about 2 cycles for that to die out, to hit steady state. But then I'm kind of averaging those last 5 to then get a good read of gain and phase.
Yeah, so you might need to do your chirp over, like we do it over, well, most of mine, when I do it over 2 minutes, but I'm not sure. It depends on the frequency range, whether that would be enough for your particular application.
Yeah, I guess if I could target a smaller range of frequencies, right? If I could target a smaller range, then I could maybe, be able to do that more quickly. This is good. I mean, what I'm doing here is I'm kind of, for the maximum gain where it finds that 180 degree phase point and that frequency, it then goes and tracks that 180 degree phase. So it kind of works pretty slick that it actually can then moves with the 180 degree phase frequency, that it then keeps it there while it's still checking to make sure to see if we're seeing any type of rise in the gain to see for instability. So that kind of works. It's just the thing that is getting me right now is that I could have other frequencies like the lead lag regressive, how I can check to make sure I'm not, exciting that. So. All right, if there's other questions or discussion, I can kind of finish up here. Yeah, future auto-tune, trying to finish that. I certainly have gotten a long way. I don't know that I'll have the time that I need to dedicate. I hope to, it's certainly not going to make it into 4.1, but hopefully I'll have something ready by the time we're getting to release 4.2. But it's coming along, and I think we're getting there. Based on what I learned here, I'd like to, obviously improve the manual tuning instructions to help out there. Then look at another big thing is kind of getting to this reliable, fully autonomous flights from startup to shutdown. It gets to a point where helis can basically invoke auto from maybe armed with the aircraft, motors interlock disabled, and let it spool up by itself, do the takeoff, go do its mission, come back, and then shut down after it lands. So Matt Keir had been helping us for autonomous auto rotation. I don't know. I'm going to put Matt on the spot and see if he's still awake.
Yeah, I'm here.
If he has an update on that.
Yeah, so I mean, a bit of an apologies there. Like, it's been pretty stale the past year. Where we're at the moment is essentially I got as far as I could in real flight, and wanted to start getting out doing some real testing. So spent some time. I've got a much bigger test frame. Thank you to the ArduPilot community. And but then obviously I just couldn't get out because of being in lockdowns all the time. So that's definitely on the plan for this year, is to kind of get out and start doing some real world testing and seeing how well real life compares to the sim.
Yeah, it's always fun. Yeah, no, that's great. I did have another user who is in Italy, and he has, I'm not sure, maybe I'm speaking out of turn, but he's actually done some, he's been doing some full autos to touchdown. So I'm interested to see kind of the methods he's using. He is using ArduPilot, so I'm hoping to kind of drag him in to see if he can to help us along. So maybe we get working
that would
with
be
him.
really cool.
Yeah.
Bill, I had just something I thought of looking at the chirp method. I noticed on one user that I helped with their Trad Heli setup, that to get around the rotor vibration, they'd ended up quite softly mounting their autopilot. And I was looking at that setup thinking they probably had a roll mode or on their mounting system that was probably getting down towards the order of about 15 hertz. And that, I mean, what's the impact of that on the roll tune? I guess it would just show up like a regressive mode, and it would take it into account if they ended up with the oscillation mounting system.
Yeah, I've changed my tune. I know I've changed my thoughts on how we handle vibrations. I'm really since the whole harmonic notch came about, I've worked hard to basically pull most of the vibration out through the harmonic notch, basically going on the 1 per rev, the end blade per rev, and the 2 end blade per rev frequencies, and that pretty much pulls out a lot of the noise out of the control signal. And so then you're just left with the feedback instability modes that you might be exciting. So yeah, I do go with a more firm mounted controller, so as to kind of keep the looseness of that mount from interacting. I mean, the big thing is controlling vibrations is kind of one of the huge things, and trying to maintain, find a good spot on the heli where you're going to get low vibrations, either due to frame or the mounting.
Yeah, and also making sure that all 6 degrees of freedom on that isolation mount don't coincide with a rotor fundamental or the
right.
harmonic.
You don't want to, yeah, exactly, yeah. And I mean, if it does, well, the rotor, yeah, if it's a rotor regressive mode or feedback stability mode, yeah, that would not be good because we don't have enough, don't have the ability to notch as many modes as we want. I mean, we still have that other static notch, which could be used, but yeah, definitely have to keep it from being exciting that the mount. So yeah, and I guess my last point there is just to clean up the trad Heli specific files and improve code efficiency. So it's kind of a long-term goal there. So that's pretty much all I got. And if there are any other questions, I'd be happy to answer or discussion.
That was absolutely fantastic. Thanks, Bill. It's really great to see the progress on the auto tune. I think a lot of Heli users are going to be so pleased to be able to get the tune right with less risk to the aircraft and a better result. That's brilliant.
Thank you.
So any final questions before we move on?
Yeah, Bill, awesome work, man. I know it's a huge marathon to work through an auto tune like this. People try and do auto tuning of PID loops a lot, and I think you've sort of, like Helis in particular, like multi-rotors are incredibly simple and as a control as far as a control problem goes compared to the Helis, and I think you've done a pretty good job of sort of showing the level of work and understanding that needs to go in to break a problem like this down and actually make it easy for a novice that has no understanding of controls to do a quick auto tune and have an aircraft that's flying well. So yeah, thanks a lot for all the hard work from everybody, I'm sure.
Yeah, thank you for your help as well and guiding me along different roads.
Often the wrong one.
No, it's all, especially the knowledge of the knowledge of the control loops is definitely helped a lot because and then how each of the gains impacts the response. It's definitely, your understanding is definitely very, you're the expert, so it's great.
All right, thank you very much, Bill.
Right.
So I'll just switch